I'm back. Section A.2. This one's on exponents, roots, and rationalizing denominators. Let's just quickly review the exponents rule. Let m, n, and b be any real number where b is not 0. Then when you multiply like bases, you keep the base and add the exponent. When you divide like bases, you keep the numerator and use the opposite of the denominator. When you raise a power to a power, you multiply the exponents. And if there's more than one term in there, we're just going to distribute q times each one. So it's a to the mq, b to the nq. Any base to the 0 other than 0, remember we're not letting base be 0, so any base to the 0 other than 0 is 1. And b to the negative m just means, yes, I want b to the m, but I don't want it in the numerator, I want it in the denominator. So let's just do some quick examples and review. 3 squared means 9. Negative 3 squared means, oh, leave that negative alone, it's not in a parenthesis. So it says my answer is negative. It means 3 squared is negative 9. In math, it is understood that if you don't see a parenthesis, the sign is not included. So negative times 3 to the second really means negative parenthesis 3 to the second. Now, in the red case, notice the negatives inside. And 2 negatives, when you're multiplying, will create a positive. 3 to the third is 27. Again, ignore the negative sign because you don't see it in a parenthesis. So I have negative times 3 cubed. Same philosophy, it's understood that that's a parenthesis without me writing it, is negative 27. And negative 3, when I cube it, is also negative 27. So notice when you have an odd exponent and you make a sign error, you live. But when you have an even exponent and you make a sign error with that negative, you die. Because negative stays negative. The only way for a negative sign to turn into a positive sign is to be included in a parenthesis and have an even exponent. Now, let's do a little investigation of why 5 to the negative 2 would be 1 over 5 squared. Well, what does a negative exponent mean? It simply means take the reciprocal. That's all the negative means. Take the reciprocal. So I was 5 over 1. I'm now 1 over 5, which indeed turns into 5 squared. So when we see a negative exponent, it's about position, it's not about sign. The positive power is the correct power on the base, it's just in the wrong place. 5 to the negative 2 is not on top, it's on the bottom. 1 over 2 to the negative 3 is not 2 to the third on the bottom, but on the top. 2/3 to the negative 4 is really do the reciprocal, 3/2 to the fourth. Notice when I have that cute little negative, no parentheses, so the negative stays, but 5 to the negative 2 becomes 1 over 5 squared. The negatives stay. 1 over negative 2 to the negative 3 is 2 cubed over 1. Notice the negatives stay when all I'm doing is rewriting the exponent, because an exponent, when I still have it, does not change the SIGN. So now let's look at some problems. 3 to the negative 2 is really 1 over 3 squared. 5 to the 0 is 1. Negative an odd number of times is negative 1. We have negative 1/9. 3 to the negative 3 is 1 over 3 cubed, and negative 2 squared is a positive 4. 9 to the 0 is 1. We have 4 over 27. What are you going to do here? Everybody needs an exponent, and we distribute. So we get 3 times negative 3 is negative 9. We get negative 2 times negative 3 is 6. We get negative 3 times 1 is negative 3. So we get b to the 6th over a to the 9th, c to the 3rd. For problem example 6. Same idea, only now I've got a denominator, so I have to distribute even in the denominator. So I get x to the 16, y to the negative 8, z to the negative 4. I rewrite. Positive on the bottom is negative on the top. Negative on the bottom is positive on the top. So negative on top is positive on the bottom, and so on. Over here, 2 for 1. I do the cube. A negative cubed is negative. 5 cubed is 125. A to the ninth, b to the thirds. Now I just multiply. Negative 2 times negative 125. Add my exponents, add my exponents. Over here, I have to play the game twice. A negative squared is positive, so I get a 9. A squared, b to the 8th. A negative 3 times is negative. 2 cubed is 8. A cubed, b 9. Now multiplying negative 72, a to the 5th, b to the 17th. Now what happens when I have a fractional exponent? I'm going to beg you to please learn these. It will make your math, science, econ life easier. What does 8 to the 2/3 mean? It means you're the cube root of 8 squared, or you're the cube root of 8 squared. Now, when you're simplifying and you have a perfect root, I think it is wiser and more efficient to find the root and then apply the exponent. And since we're making all of these perfect, you're going to see me, what's the cube root of 8? 2, and squared is 4. What's the fourth root of 16? 2. Cubed is 8, but it belongs in the denominator 1/8. Notice the negative sign. It's not in a parenthesis, so my answer will be negative. It comes along for the ride. I want the square root of 25, which was 5. 5 to the negative 3 means 125, but not on top, but on the bottom. Negative 1 over 125. I'm going to get to that language in just a second. What happens when you see this mess? Well, to me, the easiest way to do a problem like this is just to get everything to the numerator. Remember, a positive exponent means you're in the right location. All a negative exponent means is you're in the wrong one. So positive on top is negative on the bottom. A negative exponent on the top would be a positive exponent on the bottom. A positive exponent on the bottom is a negative exponent on the top. A negative exponent on the bottom is a positive exponent on the top. So, when we come here and I look at this problem, I want the 3 and the negative 4 to move to the numerator, so the 3 becomes negative and the 4 becomes positive. And now take out your calculator for all I care. Just do that sum. But if you want to know how to do it, because you really need to know how to do this, I go ahead and add the integers. The common denominator is 6. 3 needs a 2. 2 needs a 3. And 1 needs a 6. When I add it up, that's 9 over 6, which is 3/2. So all this malarkey turns into x to the 3/2. Moving on, we will continue. We're now going to move into roots, and we're going to discuss those. So roots. When roots are not perfect, what do I want you to do? I want all the bases, including the numeric ones, written in the lowest terms in base exponent form. Then you'll write each base twice, numerics included. The first time you write the base, you use the highest multiple that's possible in the exponent that you have of the index. For the second one, it's whatever was left over. Remember, negative stays negative and positive stays positive in an odd root. And what we'll find out is we'll divide the exponent into the exponent that's a multiple to see how many we can take out. And the one that was not a multiple will stay in. This, of course, makes more sense when I use the examples. All this stuff is in your notes, by the way. Remember, the root is called an index. This is your exponent, your base, and the symbol itself is called the radical bar or the radical symbol. So I know 16 is not a perfect cube. So the first thing I do is say, what is 16 2 to the fourth? Now, what is my index? My index is 3. 3 goes into 4 ones, so I get 3 2 to the third and 2 to the 1. 3 goes into 8. 6 is the largest multiple, and there's 2 left. The largest multiple of 3 that goes into 10 is 9 with 1 left. So what's going to happen? I take out the negative. I can take out one of those, and when I divide 3 into this, I get 2 of those. When I divide 3 into this, I get 3 of those. And now you see what's left up there stays on the inside, so my answer is negative 2. X squared y to the third, the cube root of 2, x squared y. One more stupid example like this, because you should have done these in Algebra 2. He's not a perfect one, so I wrote it as 3 to the fifth. 4 goes into there once, so I have 3 to the fourth, 3 to the 1. 8 is the largest multiple. X to the 8, x to the 2. Oh, that's exact multiple. The largest multiple of 4 is 24 with 3 left over. So now I'm ready to play the game. Index into exponent says I can take out 1. Index into exponent says I can take out 2. Index, oh no, there's a mistake. Index into exponent gives me 2. Index into exponent gives me 6. And so I'm left with 3 x squared y squared z to the 6th, the fourth root of 3 x squared z cubed. Now, when we want to rationalize a monomial in the denominator, we need to remove we need the exponent to be a multiple of the index. So a square root 2 needs a square root 2. A square root 3 needs 3 of those 3's. Fourth root of 2, I need 4 2, so I need 3 more. The fifth root of x, I need 5 of the x's, so I need x to the fourth. So when I see the fourth root of the 4 over the square root of x, I multiply by square root x over square root x. What is square root x times square root x? It's just x. And I get 4 root x over x. Now what happens when I see 7 over the fourth root of x? Well, I have 1, so I need 3 more. And when I do the fourth root of x times the fourth root of x cubed, I get the fourth root of x to the fourth, which is equal to x. And so my final answer is 7 fourth root of x cubed over x. Now, one last thing to learn. What happens when there's a binomial in the denominator? Well, we have to use the conjugate because I'm only going to give you square roots. And when you multiply by the conjugate, you get a difference of squares, and that gets rid of the radical in the denominator. But my college professor in college gave us a problem that had cubes in the denominator, a sum or a difference of cubes, and we had to know how to multiply by that. So if you're whining, remember I could make you do that. Your professor would make you assume you know it. So 4 over 3 plus root 5. What's the conjugate? 3 minus root 5. Always multiply the conjugates. 9 minus 5, you get 4. Before I distribute, I see, can I reduce? Walla walla bing bang, I was able to. The next one, I'm going to use conjugate again. I'm going to do the conjugates. 49 minus 2, 47. 5 and 47 don't reduce. So I go ahead and distribute. And yes, that luscious looking answer is our answer. Now, I have practice problems that you could do. You can freeze this page on your calculator, but I have 10 that you could try if you choose to. And I'm just going to have you do root 3x times 3x times 3x do a couple of the exponential things. Number 5, the one with the fractions. Number 6, where you've got to do the root and then the exponent. 7 and 8, where you've got to get the base and exponents to be multiple. 9 and 10, where you're going to rationalize. Now, I'm going to keep the solution page over here for what I'm going to get. Just a bit of peanut butter back there. It's how I make myself a document camera. Yeah, don't ask. So number 1 should be 27x to the cube. Number 2, if you did it properly, 1 over 25. Number 3, if you distributed and rewrote, you're fine. Number 4, if you cubed the second quantity properly and got -8, a cubed, b cubed, you should be fine. Number 5, if you rewrote it and then you got a common denominator, you should be okay with x to the 5/4. Number 6, since it's a perfect root, if you rewrote the root and then the exponent, it should be okay. 7 and 8 are just following along with what I did in the classroom, where, as I showed it, where I'm going to have 3 to the 3rd, and I see I can only get an x to the 6th and a y to the 3rd, so I have the extras, and I go out and ahead and divide index into exponent. Same thing goes on with number 8. When I'm looking for multiples of 4, I need a 2 to the 4th, an x to the 12th, a y to the 4th, and a z to the 4th, and I have those leftovers. Then my rationalizing, I see that it was a cube root, so I only had 1, so I needed 2 more. And then I rationalized the binomial. I ended up with 5 minus 7, which is a -3. Oh, but -3 went into 6. So I went ahead and reduced, and then I distributed. So again, you can always freeze this and check it. If you have questions, if you did these and you're confused, you can always contact us because we will present you our information.